Hi everybody, this is Chemistry Week 3. This is actually going to be an in-person session as well as the lab. For the people in the internets at home, make sure you do print out your sheets and do that. A couple housekeeping things. Some of you guys got K-mails from me saying that you had a D and or an F and you're required to be here. But if you looked at your grade and you had an A or a B, apparently even though I took names out, it sent it to everyone. And so, that's my bad. I answered the 40 K-mails of the kids that didn't need it. But for whatever reason, one thing I do want to point out is every single Monday in the morning before 12, whatever, I go into your class, I zero out everything you were supposed to do the week previous. Alright, so it's zeroed out. If you did it, great. You get the grade. But if not, you get a 0. And then at the end of that, as soon as I'm done, there's nothing in the Dropbox, and I graded everything. I pull exports of the grade, and I save a copy. Then those if you have a D or an F on that sheet, you're here. Now some kids, like right after I sent out that, they're like, oh, I did the quiz real quick, and I turned this in real quick. Yay! Like, I don't have a D or an F. I'm not playing the game. So if you have a D or an F on that Monday, you're coming in. You can have an A after that. I can care less. If I don't put a number or a set time on that and stop at a certain point, it's all over the place, guys. Like, it's just, whatever. And I need to have at least some sort of, like, okay, deadline. You had to work through the weekend, Monday morning. So just letting you know. So keep your grades up. That's really bottom line. Most of you guys have good grades, so don't even stress about it, honestly. Thank you for coming, because I look around and I see a lot of students with good grades. The D's do not have a D or an F, and they're here, so thank you guys for showing up. If you are here in person, I already told you what to do for number 1, right? Okay. At home, make sure you guys get that complete. Number 1 needs to be completely completed and turned in for credit. The people here, they know what they're supposed to do for question number 1. Alright, so let's get going. Just so you know, if you weren't here, unfortunately, I put it on this video and it's Apple and stuff and YouTube, but for whatever reason it's not popping up. So it took the media away. This was a video. If you want to look it up, it's like hot air balloon, swinging from hot air balloons or something like that. There's a cool little video I found, but we'll just get into this stuff. So the essential concept for this class, which you guys all don't have to worry about because you're here and you're doing it right now, is what is the relationship between gases in regards to its temperature, the pressure, and the volume, and how do each relate to each other? Okay, because this whole lab, and we'll see a video in a bit, is based on, where'd you put my balloons? Jacking my balloons. Basically, what you need to do at home, as well as here, you're supposed to take your balloon, and you're supposed to take at least 2. You blow it up. Now, what did I just do? Don't tell me I blew up the balloon. I swear that is not the answer, guys. You're killing me. You guys are looking around and going, he's blowing up a balloon. What did I do? Tell me in scientific terms, what did I do? Good.
You increase the air pressure inside the balloon.
By adding air.
Oh, yeah. Okay.
I added air. I literally forced air into the balloon, and now there's an air pressure. This right here is an exact circumference of whatever it is. You have to make sure you guys, when you're at home, you need to measure around the center diameter and make sure you write that down. It's very important. So what we're going to do is you would measure around the top, and you would mark whatever it is. Whatever the circumference is. Okay? Let's just say this was 12 inches. Okay? At home you'll have various dimensions based on the amount of air that you put inside your balloon. So you have 12 inches. Now, this is an exact, what happens is right now it's in equilibrium. The amount of pressure inside is pushing against the air pushing on the outside. There's literally air on the inside going, what? I'm going to fight you. And the air on the outside are going, what? I'm going to hit you too. And they're like fighting back and forth, and now it's at this exact size. Now what happens to anything as you cool it down? Say I'm going to change temperature. So I'm going to make a cool balloon. Yay! And I don't know how you're going to be able to see this really at home. Show up here. It's better. So right here. So let's say right here. I just blew air into here. Now a quick little biology / earth science thing is, what did I blow into this balloon? What did I blow into it? Don't say air.
Carbon dioxide.
Okay, I did blow. I'm just going to do this as a quick little side note. Yeah, I did carbon dioxide. What else? This is the fun part where you guys have to remember what you learned in like earth science. What's in the air? How do you stay alive?
Oxygen.
Thank you guys very much. Is it an oxygen singular or double? Single oxygen, not so good for you. You need to have the two, okay? Our body likes the two oxygens to hang out with each other. What else? And by the way, this is a trick. This is actually what is the most abundant gas in our atmosphere? Nitrogen. So technically, this is mostly nitrogen. A lot of carbon dioxide since it came out of my lungs, and probably less oxygen. Okay, just want to make sure we point out what's in there. But in general, it's a gas. Does anyone know how gas is, like, in general, how gas behaves? Like my 2-year-old where he just whines all the time right now? Behaves horribly. But how does gas behave? How does that behave in there? What's happening? Are those just sitting there staring at you? But hey, look at me, I'm a gas. Okay, what happens?
They're just in constant movement around the flow.
Yeah, they're just this way, this way, just bouncing off each other. Every single collision is considered perfectly elastic, where it doesn't lose any energy as they bounce into each other. Okay, now this is a gas. Now, if I had a solid like this, they would all be in a perfect line. There wouldn't be barely any movement, yada yada. If it was liquid, there would be little movement, kind of slipping over each other. Gas, they literally just bounce all over the place. That's this. So we're going to talk about 3 things that affect this. Okay, we're going to talk about its temperature, or change in temperature, change in pressure, and then we're also going to talk about how that affects the volume, or the change in the volume. So how they affect each other. So, and by the way, I guarantee you guys all know all this. I guarantee it. Ready to go? Let's see if we know this. What do you think happens to this if I warm up the air inside of it? What do you think? It'll inflate, which means expand. Because, can anyone tell me why they think that'll happen? That if temperature increases, that the balloon will actually expand.
Because the energy is increasing?
And what happens when energy increases?
The pressure does?
What it happens specifically is these molecules get super excited. When you warm them up, they go woo, and they get all like crazy, and they like bounce around, and start hitting things, and they start going crazy. So they start slamming against this wall more and more and more. And what happens? It gets bigger because this is elastic. It allows me to do this. Now, if this was like a metal box, nothing happens. Guys, get that? We're using a balloon so you would see that expansion. So you're right. Temperature goes up, it inflates. What happens if temperature goes down? They get lazy. They become teenagers, okay? And they actually stop moving around as much, and they sleep more. You know what I'm talking about. And it starts deflating, basically. All right. Now, if we already went over this kind of a little bit. Temperature increases. What do you think happens to pressure? As this expands, what do you think happens to the pressure inside, more or less?
More.
Wow, you guys already know this. This is amazing. Good job. Okay, so what happened to the volume? What happened as it increased? The volume did what? It got bigger. Wow, you guys are amazing! Why are we even here? Let's all go home. Bye. Alright, so let's go back to this. So the essential concept is looking at the relationship. So you guys probably right now can fully answer this essential question. So that's awesome. So let's talk about atmospheric pressure. Just kidding. Let's go back to atmospheric pressure. Alright. So the gases in the air exert a pressure called atmospheric pressure everywhere. In this room, there's atmospheric pressure pushing against everything. Do you guys ever like really mad at your parents or your guardian and like you slam the door and it just goes slam, and it's like this huge like loud noise? It's because your window is open and you didn't like realize your window was open, and then like it slams and you get in trouble for it. Now my wife this weekend told me that she got in trouble for that one time. She like slammed the door and just it slammed. Now if that window was shut and she slammed the door the same way, it would not have slammed. Because air is trying to move places, and the air would actually stop it, and it would slow it down before it actually created a slam. So, it's everywhere, even in this room. In a tornado, you guys know what you're supposed to do in a tornado? If a tornado is going to pass through your house, what are you supposed to do? Okay, you're supposed to go underground, yada yada. What are you supposed to do to your house?
Open the windows.
Open everything. It's weird, right? You're supposed to open everything. You want to make sure the pressure in the house will stay the same outside. If you do that, there's a good chance if the wind, and it won't just pick up your house and throw it around like a balloon, the wind will pass through your house. So you want to open your windows to keep that pressure, same as here. The pressure outside right now is different than in here. If I open the door, do I feel wind coming in? Do I feel wind going out? You can always even test something like that by putting a balloon next to your door and opening it. Didn't move. Pressure is the same. And if pressure is different, it would either push the balloon in your room if there is more pressure on the outside rushing in, or it would push the balloon out if it was the opposite. Alright, cool. Atmospheric pressure is the result of the fact that air has mass, which everything has mass, okay? Everything, except for me. I'm not that massive. Don't bring it up. I'm sensitive right now, but I will. And there's an exerting force of gravity basically on everything. By the way, if you need this later, let me know, and I can even send this out to you guys through an email or something, okay? Alright, so there we go. Knowing the atmospheric pressures, you can predict changes. In earth science, we're talking about difference in changes of pressure. So, example, on a day it's really windy, well, you have an area somewhere away, like out in the desert, that right now has a certain pressure, and then over here it's a less pressure. So what happens is, as the pressure change happens, you'll get wind coming from the desert out to this way, Santa Ana winds. That's what they are. It's basically that air going, we really need to fill this area quickly, because all the air is starting to go away. And it's bringing it in. There's more pressure there at the bottom, like right here, than there is if you go to the mountain, too. Okay, so this is gravitational force. We have one atmosphere here, down at the very bottom, and as you get to the top, you have a different level of pressure, less pressure as you go higher. But believe it or not, when you stand outside and you do this, you're holding up air from there all the way to the top of the planet. Gravity of it, but whatever. We'll just say how strong you are. You're amazing. But that's what you're doing. You're actually holding up that column of air. So when we talk about atmospheric pressure, it changes with altitude. Do you guys know what altitude is? Height. From the ground. Okay, so altitude is if a mountain, you're at the very top. It's cold, less air, it's hard to breathe, yada, yada, yada. Closer to the sea level is where it's at, because if you think about it, air is kind of like I don't want to say it's a liquid because it's not a liquid, okay? But if you look at it, you can actually, it acts like basically like a cloud. Think of a cloud moving around. There's going to be a denser cloud here because it sits closer to the earth than it is up away, just the way gravity works. So it's better to be near sea level. Who cares about that? So here we go, just a quick little just visualization. Let me go ahead and see if I can write on this. I want to write, what color should I write in? Red, orange, blue, green, purple. I heard blue first. Bam, purple will be next. Alright, so if I'm right here, and I'm making my way up the mountain, as I go up the mountain, I'm going to see less pressure. And that's where you see right here that there's a certain amount of pressure here, and then it changes, becomes less as you get to the top. That pressure difference, if your body's not used to it, you can actually die. Like your body is not used, you will pass out. That's why people who travel up to high altitudes, they have breathing apparatuses and carry oxygen on their back. They need to, or they do altitude training, like fighters and stuff. They'll actually go to the mountains, even in the area up in the mountains. They'll actually learn, they'll go up there and they'll fight up there and they'll run up there, and they're getting their body so used to having a lack of oxygen. So when they go to Vegas and when they're sitting there like at pretty much sea level or whatever, close to it, their body won't react nearly as bad because their body's used to the lack of oxygen. They're actually in better shape because of it. Olympic athletes do that as well. Like us, teachers, we do that. Right? We train, altitude training before we start teaching. Oh yeah. Alright.
I'm so active.
By the way, hey, this note thing doesn't allow you to embed YouTube. Embedded. It's like, sorry, haha, no birdie.
Lame.
I hear you, brother. Okay. Alright, so lower pressure or dropping the pressure indicates a change in weather. We don't care about that. That's more, okay, this is something else I took from Adjective. Okay, so this right here does it. There's something called gas laws and how they indicate or they go together. We're going to get to a point where there's going to be some formulas. Don't get scared, okay? These formulas aren't that bad. They usually give you 2 out of 3 answers and you just plug it in and get the answers. We'll get to that. So these gas laws were developed. Basically, it's kinetic molecular movement. That is what you just told me. All of these things are moving around. All these things are either going to slow down or increase due to temperature. The volume is going to increase or decrease inside of something if it gets more excited. The volume will change, pressure will change, everything will change because of that. Again, don't freak out if you can't write it all down. So, this is something important, Boyle's Law. Alright, Boyle's Law indicates that this guy named Robert Boyle, probably a very smart man, I'm assuming. His first name's Robert. Only people named Robert are smart, is what I hear, is what my mom tells me.
Unless they have the last name Hayden.
And they have the last name Hayden, they're even more intelligent. My mom says I'm smart. Alright, so this is what they said, and this is what Boyle said. And this is the only way to really remember this guy, is easy way, is he talked about pressure and volume. He did not talk about temperature. All these guys talk about like the same thing, kinda, and to know what Boyle did? He talked about pressure and volume. He said there's a relationship between pressure and volume. They hang out with each other. They met on Match.com or something, or Farmers Only. It was something weird. But they totally met each other, and they have a relationship. Alright, he measured the volume of air at different pressures, and he observed the pattern, and he led to a mathematical law. So, oh, that's good. You can totally see the bottom, huh? Okay, just so you know, during his experiments, we're not going to go through this, the temperature will remain the same. He kept it the same to basically get rid of that as a factor. He wanted to keep that controlled. Later, other people did not do that. So, here's a little picture of what happens when you take something of pressure with a molecule, see how they're all spread out? They have room to move around, and as you basically push down this piston, you're making them hang out with each other, get closer together. So if you're increasing the pressure, you're also increasing, if you're increasing the pressure, you're decreasing the volume in that case. In this, because it does not allow for the expansion. Remember, we talked about the balloon, it'll just expand, right? But when something cannot expand, something is set, it's not going to move, you can see it here. If I push down on the piston, I increase the pressure by decreasing the volume. There's a direct relationship. The more I decrease it, the more pressure there is. See, as pressure increases, volume decreases. So that line, it's like this. Starts high left and goes straight down bottom right. There you go, and you're going to see it right here. Here's it graphically. That's the way it looks. So the easy way to put it is, if you have a pressure right here, in the same exact model, your volume would be higher. As you increase the pressure, your volume decreases, it goes down. Pretty straightforward, right? Make sense? Direct relationship. Pressure increases, volume decreases. Alright, let's see. And there's a formula. Come on, computer. You can do it. Alright. So Boyle's mathematical law states, since PV equals K, basically pressure of one situation and volume of one situation is equal to the pressure and volume of another. So in your class, it's going to give you like these questions where it's going to say, okay, so the pressure is this and the volume is this. It's equal to, and it's not going to give you the pressure of the second situation, but it'll give you the volume. And you just plug in each one of the questions or each one of the values and then calculate the answer for P2. And that's what basically you're going to see inside of your class. So here's an example. If it says a gas at a volume of 3 liters at 2 atmospheres, so that's one situation, what's the total? P times V? 3 times 2, guys, killing me. 6. Thank you. So this would be 6. And so in this right here, you're putting the atmosphere, which is the volume, 4. What do you have to times 4 by to get 6? What? 1.5. So, in that case, we know the pressure. In that case, I don't even know if it gave it, it's 1.5. There you go. 2, 3, 4. It's V2. Represent it. Boyle's law. You're right. What it's doing is it's rearranging mathematically, basically, to get the answer. So, plug into the calculator. Equals 1.5. So, you in your head, just by knowing the fact that there's relationships, okay, this guy equals 6, I have 4, whatever that, I have to basically times that by to get 6, you're able to get this answer before I can move 4 slides over. So good job. So you're going to see that. Now, Charles' law. Now, Charles determined there was a relationship, again, not between volume and pressure, but between temperature and volume. And so let's just quickly go through this, because a lot of the stuff you guys already know. And you can see this cool guy right here. This is not me. I'm not nearly that good looking, but this guy right here. He's outside. It's warm, obviously. He has a hat on. He's got a t-shirt. It's obviously warm. And the balloon is bigger. Why? Because agitation of molecules on the inside expanded. Woo! And then you have on the other side, apparently it's cold. He's wearing a jacket and a scarf. And a hat. Even though the hat really doesn't matter if you put the other hat on, it's do the same thing. Oh, we're not going to get into that. And the pressure of the balloon actually gets smaller. So at home, when you're doing this, we did this here already, is that you take the balloons, you do a certain circumference, and you put it in your freezer. Leave it there overnight. Take it out, remeasure the circumference. Based on what we know, the volume will do one of two things. It will get, three things. It'll stay the same. It'll either get bigger or get smaller. I think we all know what's going to happen, so I want the people at home to figure out for themselves, because we already know the answer. We did it here. And then the opposite, it tells you you're going to heat it up. So you're going to put it with, say, warm water, and you're going to let it sit in the warm water. And you're going to see what happens. Does it expand? Does it contract? Does it stay the same? And you're going to write down those observations. We already did that here. All right, there's a direct relationship. And what happens is, as volume increases, it's due to an increase in temperature. So temperature increases the volume in this case. So graphically, straight line. It's not inversely related, it's actually directly related. And again, I'm going to send this to you guys in a bit, so if you don't quite get it, it's totally cool. So if we look at mathematical law, we'll go ahead and sit. This formula you definitely want to write down somewhere. And again, I'm going to send this to you guys, so it's cool. You definitely want to write that down. Because this is going to give you the ability to solve these equations. It's going to give you the volume and the temperature of the one situation, and it's going to give you only one, either a temperature or a volume of the other situation. You plug them in and you can calculate the answers, just like you did in the very first one. Okay? So, it's going to go through some mathematical changes. Okay, it's going to tell you the givens. Just going to quickly get through that. So, you just plug it in there, you just plug the variables. So you just do some math. So you go 3 times 500 divided by 4. Okay, so you're going to multiply that out and then divide by, just so you know mathematically, I'll just show it to you. I assume you know this, guys, okay? I'm sorry that you don't know this, but you multiply these together, so you'll get, in general, 1,500, and then KL. And then what happens when you divide by 4, the two K's, the Q Kelvins, will actually cancel each other out, and then you only be left with liters, which is a volume, which is what you're actually looking for. So, in case you don't, so it'd be 3.8 liters would be, in the exact same scenario, what would happen if you had the change in temperature right there. Come on, you can do it. You can do it. Come on, come on. What's funny is that if you do this on PowerPoint, there's like all these like sounds in between each. Like every time I click it, it makes sounds.
You miss those sounds.
I know, I miss them. But real quick too, you have 400. You increase the temperature by 3 liters, and we know the answer is 3.8. Obviously, it increased 2. That's a direct relationship of what we're talking about. Okay, plug and chug. Okay, come on. Come on. Okay, give it a second for my laptop or my computer just to decide it wants to work. What did you do to this thing? Okay, give me a second, I'm going to go back into OneNote. Okey-dokey.
It might work.
I broke
Close
it.
it out.
What?
Close it out and then start it.
I mean, like this?
Yeah.
Sorry guys, I apologize for the technology problems. It happens. Okay. Okay, Gay-Lussac's law is, again, there's the same exact type of relationships, but now he's using temperature and pressure. So not temperature and volume, or I'm sorry, temperature and the other stuff, or volume. They're all doing the exact same thing, but they're looking at all the relationships of each other now. So make sure if I was writing down the notes, I would just write down at Boyle's, okay, whatever it is, law, and I would just put, connects this to this, connects this to this. So it starts asking for it in the test. It'll say, well, this person was asking for the relationship between this, and you just gotta look, pressure and, this guy. Oh, is that, that guy. It's an easy way to do it. So looking at behavior, so as temperature goes up, pressure goes up. Oh, it determines. So, think about your tire. What happens, do you think, as you start driving on your car and you have an increase in temperature, what do you think is going to happen to the pressure? The arrow just moved. Totally means it moved up. Okay, so there you go. Yeah, it'll definitely move it up. That's why it's actually funny. I didn't see it happen, but I saw someone else. I saw it happen to someone else. It didn't happen to me. It's really funny. They go there and they're like putting their air in their tires, and they're like, "Cool, I totally filled it up. It's perfect." And as soon as they start driving on it, it just warmed up. It's all boom, blew out on them, and I was like, you don't know the laws of chemistry. And they're like, what? It was just funny because I was like, duh. That's why they have you at a certain temperature, because it's going to increase and decrease based on your temperature. So I thought that was funny. It's mean of me, but there's a direct relationship between the increase in temperature and the increase of pressure. Now remember, this is in a situation where you don't have something like a balloon that will expand, okay? This is something like in this room where if I start increasing the temperature in here, the pressure will increase in here. You guys get that difference? It's in a set location, you can't. You don't have to be quiet, it's cool. I'm making enough noise out here anyways. Okay, so we're going to go through the same mathematical law. If you look, it's actually identical to the last law when it comes to the actual mathematical formula, but you'll see that the only difference is that it's different variables. So, the exact same one as the last one we saw, but in this case it's using atmospheres and temperature and not the other. Cool. Plug and chug, same way. So this is actually a really good slide, and when I send this out to you guys, I highly recommend actually printing this slide and cutting it out and gluing it into your science notebook on like the left side. Because look at it, it has the formula, it has the relationship that is P goes up, V goes down, V goes up, T goes up, P goes up, T goes up, and it gives you the names. This is like your cheat notes right here. Cool? So I definitely would do that, and I'd print that out and put that on there. Alright, so guys on the internet, so I'll go ahead and let you go. I'm going to go ahead and stop the recording. We're going to go over a few more things in person, but make sure you get that lab to me in the Dropbox under the proper lab, as well as make sure you also go to your live week 3 session and go ahead and place the essential question to get credit for going to the lab. You get 2 birds, 1 stone.